So lecture 29, titled Newton's First Law, Galileo's Principle of Inertia. So we're going to get to Newton's first law by talking about the work that Galileo did, which preceded Newton's work. Notice I'm sure it was an inclined plane. But also we're going to be talking about inclined planes. So this is how Galileo made his measurements, right? By rolling marbles down inclined planes. And so what I've drawn here is an inclined plane. Do you understand the concept of it? Yeah, it's a little hill. It's got a constant slope, right? And you roll a little marble down it. Now, why would you do that? Well, because when you drop things, right, it all happens very quickly, and it's hard to make accurate measurements of what's going on with the motion of that object. If I drop a marble, it's the same as when I drop a pen, right? So instead, if you roll them down an inclined plane, then based on what the angle of inclination is, right, the lower that is, the slower the acceleration. We already know about acceleration because we talked about it in kinematics, right? So you can kind of tune the acceleration you get by changing the angle of incline. So in general, we can think of, here's the ball, right? And we of course have an acceleration straight down of minus g, right? 32 feet per second, 10 meters per second, whatever you want to think of it as. But we can't travel straight down, right? To get down, we have to go this way, right? And so we can break up the acceleration into two components. One that is perpendicular. If you think of this as this big triangle, this is the hypotenuse. We could also call that our track length, right? So our track length is also the hypotenuse of this larger triangle I've drawn with angle theta, right? And I can think of two components of the acceleration. One that is perpendicular to this track length, right?
Yes.
And so what is you can see that there is no acceleration in the perpendicular direction, right? It is not moving down this way at all, right? All of its motion is in this direction, which is the acceleration parallel to the track length, or the hypotenuse, you see?
Yes.
Well, because this green line, the perpendicular component of the acceleration, is perpendicular to this track length line, and this blue line I've drawn here, the parallel acceleration component, is parallel to it. The angle subtended by these two, and because the direction of the gravitational acceleration, which is straight down, is parallel to this side over here, right? Which I haven't really drawn anything on, but I'll put a little tick mark there. They're not equal, but they're parallel. So the angle theta here is the same as the angle theta here. Okay, it's a similar triangles relationship, and it's just because the green line is perpendicular to this, the blue line is parallel to this, and the hypotenuse of this larger triangle, right, is parallel to this side. Okay, so that means that we can write these components as follows. The perpendicular component of acceleration is just 0, right? There is no acceleration in this direction. All the acceleration is in this direction. And so A parallel is equal to minus g times the sine of theta, right? Because if this is theta, the sine of theta is the opposite over the adjacent, right? So if I take the opposite over the hypotenuse here is minus g. So if I take minus g and multiply it times the sine of theta, I get this component A parallel, okay? So that's how you might recall that the sine of theta can vary between 0 and 1, right? So if we can make the sine of theta 0, we can completely turn off all acceleration. And so that, of course, would correspond to, this angle being all the way down like this. So it's a flat inclined plane, right? It's just going to sit there, right? Whereas if we raise it all the way up to 90 degrees, right? That's making this angle go all the way up like that. That's just the marble falling straight down, right?
Yes.
So if the angle theta is 90 degrees, then the marble just falls straight down. You get the full acceleration due to gravity. So we, of course, want to be somewhere in between those two extremes. So usually, because the reason you're doing this is to kind of slow down this acceleration, right? So you don't get so fast so quickly, right?
Yes.
And so it's worthwhile to mention the small angle approximation. The small angle approximation is basically this. I'm not going to prove it, but I'll just show you. The sine of theta is approximately equal to theta for small angles, okay?
Okay.
Now, this is in radians, though, okay? It does not work in degrees. And so to do it in degrees, we would have to say something like, if you want it in degrees, you have to multiply this number here, right? If you specify theta in degrees, then you have to multiply it times pi over 180, right? To convert it from degrees into radians, okay?
Okay.
So if we wanted to, for example, consider what is the parallel, except what's the acceleration we would see on an inclined plane if we used theta of 10 degrees, right?
Yes.
Well, so if I do A parallel for 10 degrees, that's going to be minus g times the sine of theta we're going to replace with theta, right? But since I'm specifying this in degrees, I'm going to make sure I put my conversion factor from degrees into radians. And so that's pi over 180, right, degrees, which gives me minus g times pi over 18. And pi is, about 3, and so we can approximate this as approximately minus g over 6, right, because 6 times 3 is 18, okay?
Okay.
So if, so it basically it allows you to turn the acceleration from gravity into 1/6 that value at a 10-degree incline, okay?
Okay.
So things would be moving much slower, be much more easy to make those measurements. I put a homework assignment. In the homework assignment, there will be one problem that has to do with inclined planes, and it has to do with bells. So because things were hard to time, Galileo had a clever idea, right? He observed that, well, we're not really good at making accurate time measurements, but our brain is really good at recognizing a steady beat, right? If you've ever listened to a band where a drummer that can't keep the beat, it just doesn't sound right. Our brain is really good at picking up any variation in that. And so if he were to set up some bells along the track of the inclined plane, such that as the ball rolled through, it rang one of those bells, he could get the spacing of those bells such that it was a nice, steady beat. Okay? And then from that, you can backtrack a lot of information. You know those are equal time intervals, right?
Yes.
If you're getting a steady beat, that means that wherever the bells are, that corresponds to a distance at which the ball has traversed an equal time interval. And so in this homework assignment, you'll be able to think about that and how you would place the bells so that you would get an equal time interval, okay?
If there's bells, which it's running into, then that slow it down?
Of course, and it has to be a very, you have to make it a small effect. Right? So it'd be like a little, maybe a paper clip, but you could have a little paper clip such that as the ball went by, it just touched it, and so it just caused the paper clip to wiggle a bell, so it would ring. So it's not going to be terribly loud. Yes, you're going to lose some of its energy, right, as you ring those bells going down, but you can minimize that, and it will have a negligible effect on your results. Okay, so this is the inclined plane. This is how it works. It just allows us to decrease the acceleration that the ball experiences so that we can make more accurate measurements, right, of its motion. Okay? And we talked about this kind of motion, constant acceleration, body experiencing constant acceleration in some detail when we did kinematics. Okay?
Okay.
So I'm not going to really do much more of that. But I do want to consider the following. So, it's very likely when doing these experiments that you could construct 2 ramps, right? And if you did, right, we'll call this ramp 1 and this ramp 2. And if we drop this ball, right, from say a height h, right, it's going to roll down. We'll assume these corners are kind of smooth, and it's going to go back up, and we're going to observe that it basically rises back up to the same height. Now it'll be a little bit less because there's energy that's being lost, but we haven't talked about energy yet, so we can't really talk about that, right? But in an ideal world, if the surfaces are frictionless, if these corners are perfectly smooth, right, then this ball will roll down this first incline through this flat section and then back up this incline until it gets to the same height as before. And then, of course, it'll roll back down, okay? And if it's completely frictionless and there's no air resistance or anything, it'll just do that forever, okay? But I don't want to worry about that part of it. I just want to worry about the idea that if I let this ball roll down, it's going to roll back up to the same height as before, okay? Does that make sense to everybody?
Yes.
Yes? Well, what would happen if and here maybe we say that the angle of this incline here, right, is the same. Okay? So these are the same angles. But now let this second angle be less. Okay? Let's make it something like this. We have the first incline, the straight flat section, and then I'm going to actually draw the second ramp in a different color so that we know where it's at. This time, I'm going to let this ramp have a pretty shallow angle compared to what it did before. Okay? And so, if I start ball out at this height h, right, I know from my previous observations with these things that it's going to roll down this ramp until it gets to this point right here, right, because this is the distance h across. Draw that in there, right? We know it's going to roll up to here, yes? Before it rolls back. So you can kind of see, right, that as, let's call this one phi, and this original angle was beta. As I let this second ramp angle get lower and lower and lower, you can see that this point is going to move farther and farther away. So let me consider another angle in the same picture. This time, I'm going to choose it to be this one. Okay? And again, I have to get, the ball is going to have to travel far enough in the x direction, or the horizontal direction, right, to get to that point right there, yes?
Yes.
And so you can see that as I keep decreasing this angle, do I have another color pen around? Do you want to see a pen? Yellow? It's not the best color. You don't have any others? I just want to kind of consider this limit, right? I'll make it just a wee bit less than what I want to consider here. Right. That's even lower. And so you can see that, right? Well, the ball is going to roll for a very, very long time, right?
Yes.
Now I should point out that just by symmetry here, right? If at this point the ball is moving at 0 meters per second, here when it turns around it'll be going 0 meters per second, yes?
Yes.
It'll have some maximum speed at the bottom, right?
Yes.
That's when the acceleration stops, right? Now it's got no more acceleration because it's in this flat section, yes?
Yes.
So whatever its speed is, that's what it's going to have there, right? That'll be its maximum speed. And we can figure that if this, because of time symmetry, right, its maximum speed will be the same here at the beginning of this ramp, okay? Which means that during this whole period here, right, we'll just call it Vmax, right? And so you can see that as we lower this ramp down, right, how long is it going to take for this ball to roll up to this height if this angle is 0? So now I'm considering the case of, what about a 0 degree ramp, right? That's a terrible line. I should have just got the ruler out again. It's right here. Just being lazy, right? For the 0 degree ramp, right? The ball is just going to travel on with that maximum velocity that it had at the bottom forever and ever, right?
Yes.
Do you see that?
Yes. No, there was for friction.
No friction. We're assuming there's 0 friction, okay? And so this ball is going to roll on forever and ever, okay?
Okay.
But see, this is I don't know for a fact that this is how Galileo figured it out, because we have the benefit of having seen, you know, space movies and stuff, right? So we know that if we were like in outer space or orbiting around the Earth, right, where Earth's gravity is canceled out because we're falling, right, that if I take a pen and I toss it to you, it'll just keep going in the direction that I tossed it forever and ever until somebody catches it, right?
Okay.
You know, if you saw the, what was it called, the Sandra Bullock movie, Gravity, I think,
Yes.
right? The guy, he got away from the spaceship and he's floating out, right? I mean, it was a real problem because if he didn't have a way to, you know, some thrusters or something to get back, then he's just going to float out in space forever, right?
Yes.
Because that's how things work in space, right? If there's no gravity around you, then you're just going to keep traveling on at whatever speed you happen to be at, okay?
Okay.
But Galileo wouldn't have had any of that, you know, movie insight because he wouldn't have seen any of those movies, okay?
All right.
So, you know, the prevailing view at the time was Aristotle, you know, who tried to explain why things move, right? He thought that motion was like the natural state of things, right?
Yes.
Whereas Galileo discovered it's really the change in that's important, right? So in this case here, right, when phi is equal to 0 degrees, right, delta v is equal to 0. So what does that mean? That means that the velocity never changes, okay?
Okay.
And so this is the principle of inertia, right? It's the idea that, let's see, an isolated object with velocity v does not accelerate. Well, that's one way to say it, right? It doesn't matter what the velocity is. If velocity is 0, it's going to stay 0. If the velocity is some other number, maybe this maximum velocity we got at the end of our ramp, right, in our inclined plane, then it'll stay at that velocity forever, okay?
Okay.
And so this is how you can kind of see that coming about, right? Just by making this observation that when you roll this thing, it'll roll back up until it gets to this height. Now, he doesn't know why that is. We'll understand why that is. We'll talk about that, okay? I don't want to jump to that too soon, so I'm not going to explain why that is. But it's something that you can observe. It's a little bit like when you bounce a basketball. If you bounce a basketball and you threw it to the ground and it went, really, really high, you'd be like, well, that's not supposed to happen. Or if you tried to bounce it and it only bounced like a centimeter, you'd be like, well, that's not how it's supposed to happen. You expect it. If you take the ball and you drop it, right, it at most is going to bounce back up to the height that you dropped it from, right?
Yes.
If it bounced higher, you know that maybe you gave it too much, you gave it a push or something, who knows? It just doesn't seem right. But this idea, right, of things, inclined planes, balls rolling and then rolling back up to the same height and then they stop, right, makes sense to us. And if we change this angle, then it takes a longer time, right, before it reaches that height.
Yes.
Because this distance is increasing. And if the angle is 0, now the distance to get back up to that height is infinity, which means it's never going to get there, which means its velocity will stay unchanged. Okay? And this is the idea behind the principle of inertia. Okay?
Okay.
Other aspects of inertia we'll talk about in the next lecture when we talk about Newton's second law. Okay?
All right.
Because there's another idea associated with inertia in that, what we would call a heavy object, right, it's hard to change its state of motion, right? If you have a big boulder, it's much harder to roll that off a hill than it is a little tiny pebble, right?
Yes.
So, but I don't want to get into mass yet, and that does have to do with mass. They would have thought of, weight or weightiness, right? They didn't have these formal definitions back then, so they wouldn't have distinguished between weight and mass like we do today. But again, that's getting ahead of ourselves. This is really all I wanted to focus on now, is this idea that isolated objects, right, meaning there are no interactions, right, there's no ramp to climb, right, there's nothing to bump into, maintain their state of motion. That's the natural state of it, right? If something is moving, it will just keep on moving. If something is staying still, it'll keep on staying still. And of course, we have to throw in reference frames here. You always have to remember everything is relative, so you have to think about what reference frame you mean that by, okay?
Okay.
But within the same reference frame, the laws of inertia, or the principle of inertia holds. Okay.